in this medical domain, what are the chemicals people are using? This is really very costly. Small amount also very costly. Okay, and whatever the testing people are doing, it is through the different standard technique, and there you lot amount of the chemicals, and that way costing will also be very high. So these are the issues, so we have to tackle that. Now for that, that's why today we want a patient specific prevention and intervention strategy. It should not be very general, it should be a patient specific. Okay. Second one, early detection protocol to identify the disease when it is easily subdued. So the early detection protocol we have to so that the disease process can be decreased. And another one is that another area, technology allowing for the long lives in the company of the disease. As a good neighbor, without sacrificing the quality of life. With a tumor, the person, the human, he will have a quality of life. So the disease should be a neighbor, it will give a company. So that actually we require the technology. Okay. The development of the miniaturized wearable, implantable, biomedical, wireless sensors for the personalized healthcare and beyond the hospital application. Again, this is the another domain, it is coming up beyond the hospital application, patient in a remote places, but his that clinical data will reach through the mobile, through wireless transmission and all these things. So these are the very vast topic. Decades of science and engineering knowledge are now converging to provide the tools through the micro and nanotechnologies that enables the manipulation of the biological system at its length scale. And that's why it is now today these two are merging together. To get the new device, to get a quality of life also, and all these things. Now in the BioMEMS, already Professor Maiti told why it is so important, because the similarity in size and the organization of the common structure between the micro nanoscale device and the biological species. If you see the MEMS device, it is in this micron domain to submicron domain, and if you see these DNA molecules in the nanometer scale, virus, then smart, and here you have a bacteria, biological cells are also in this domain. So this device is very much compatible to diagnose all these things. Okay, cells. It is say a biological cell, dimension is about 10-20 micron. So it is best suitable for the microfluidic device. Okay, to culture or to detect its various characteristics and all. Earlier, in this domain, the devices are working to get this the characteristics of this bacteria, virus, DNA, and for that you require a lot of chemicals, lot of samples, and all. But if I use a MEMS structure, a microfluidic device, then your sample volume will be reduced, your chemicals requirement will be reduced and all. Today, you must have seen the blood sugar the detection unit. It is very small. You have a electronic system, but there is a one small what we call it is syringe or capsule kind of thing, and there you just put a drop of blood and it will give what is the sugar level. Okay, how it is being done? It is by the electrochemical process. So inside that you have a strip, not the capsule, you have a strip, small strip is there, and that you have to put it, place it in the electronic device. What is there in the strip? you have a 2 electrodes only and a small channel. 2 metal electrode and a small channel. If you place the blood over there and just a drop of blood, through the capillary action it will go inside, and at that place you have some enzyme. That enzyme will react with the glucose present in the blood, and that chemistry involves it is a electrochemistry, and by that process it will generate some current, and this current you have to detect, and the current is proportional to the level of the glucose. If the glucose level is high, reaction will be high, current generation will be high, and that way it is detected simply. But in a conventional way, 1 drop of blood you cannot go for the testing process. Today still some of the clinical laboratories, they have that things, they require this much amount of blood, but just with a drop of blood you can determine what is the sugar level. Here your sample volume is reduced, your enzyme, that enzyme very specific to that sugar, it is very costly. So in the general process you require a lot of chemicals or enzymes also, that's why it is costly, your testing is very costly. But in this micro device you have a very small amount of enzyme, not only small amount of blood, but the enzyme volume is also very small, that's why total cost will be reduced. Okay. So in the similar way, these devices, if we can miniaturize this device, you have a lot of advantages. So BioMEMS here, so it is a label-free process. This is another important one, label-free. What does it mean? Generally, in the biotechnology, in the biochemical process, if I want to detect some reaction things, then I have to tag that molecule with a fluorescent molecule, so that I can detect through the fluorescent microscope, you can detect where those molecules are going, what is the reaction and all these things. This is called the labeling process. By labeling, antibody antigen, you have to mix it with the antibody and antigen reaction, and there you have to put that fluorescent. And this antibody antigen reaction is very, very specific to the sample. Okay. And those antibody antigen, again, it is a very costly, and that's why if I can do some testing without any labeling, without any antibody antigen reaction, then it is called the label-free detection. Small volume of the reagent, CMOS compatibility, that means where it will come. Just for your example, the blood glucose measurement, as there is electrochemistry, you will get a current, but the level of the current it will generate, it is in the micro to nano ampere level. So now today in the CMOS process you can easily amplify and you can detect that very accurately, you can detect it. So here you have a CMOS technology also. Reduced time for the diagnosis, safe reusability and miniaturization and portability. This is another important thing, because you have to do it out of the hospital. Okay, so in a remote place you can bring it, you can go and you can do this all the testing. Now in a broad sense, we just divide the biomedical MEMS device, BioMEMS devices in two different categories. One is called the biomedical MEMS, that deals in vivo within the host body. Precision surgery, we require some, for the robotic surgery we require some instrument. Drug delivery at the point of care. Okay. Prosthetic devices, biosensors and other physical sensors, and biotelemetry. Whereas for the biotechnology MEMS, it deals in vitro with the biological samples, say for the rapid diagnostics, gene sequencing, drug discovery, pathogen detection. So, but it is a very, in a general sense, this is the two different categories. So I am skipping that nanolithography. I am skipping that Uh, Now, implantable wireless microsystem uh, incorporate the MEMS based transducers, have onboard power supply or powered from outside by the inductive coupling, communicate bidirectionally through RF interface, onboard signal processing capability, constructed using the biocompatible material, use advanced packaging technique. So some of the transducers we can keep it in our body. Okay, it is an implantable device. Suppose many of the devices are coming up which can be implanted inside the body for sensing the different things and all. And for that, what you require for the implantable device? It has to be operated. So you require energy, you require a battery, and battery should be long-lasting battery. Okay, so you require a power or energy. Second one is that communicate bidirectionally through the RF interface. So bidirectional means from the outside I can control the device, implantable device, and whatever data it is generating, that will also come to my computer. So it should be bidirectional process. Have an onboard signal processing capability. Okay, because many of the signals that will get it, its strength is very, very small. Okay, so at that place itself, you have to do the processing, you have to amplify, you have to digitize, otherwise you cannot send it outside. So you have to digitize also. Okay, so onboard signal processing is required. This is a very important biocompatible material. For the other applications, we do not have to bother about this one, but this is a most important parameter, biocompatible material, if it goes inside the body particularly. Okay, and if it is outside, say cell culture, DNA amplification using this BioMEMS, it is done in vitro, it is outside the body, but still there also you have to see whether the cell can be will be live using these materials or not. So in the some sense you require the biocompatibility, but if it is an implantable device, all the parts has to be biocompatible. Okay. And for that, various polymer materials are being coming up. A lot of research are being done. And packaging techniques. I don't have to say anything packaging, because you have in the yesterday's class, Professor Nayak has already mentioned that. So for this device also it has to be. Now some of the problems are still there. Transducers are interfaces between the tissue and readout circuitry, and their performance is critical to the success of the overall microsystem. Long-term stability also is an issue. Okay. Now transducer suffers a poor signal to noise ratio and thus requires onboard interface electronics. Okay. Post or integrated CMOS processing or the hybrid processing technique is used for the fabrication of the microsystem. Power consumption is a major consideration, particularly for the implantable devices. Thus DSP is done outside the body generally, but today it is most acceptable if the DSP is done inside the body and then the data is transmitted. Packaging and the encapsulation is a challenging task. It must accomplish to number one is the product electronics from the harsh environment while providing access windows for the transducer to interact with the desired measure. Okay, so it has to be protected from the harsh environment. Your pH level may be different, but that material, the device material should sustain that pH level, and that pH level is also changing over the time. Okay, so it has to be, we have to consider that. Protect the body from the hazardous material in the microsystem. So whatever material will come, that also should not affect our body. The body environment should not affect the microsystem. The microsystem material should not affect our body. Okay. The second one is the choice of power source. Depends on the implant lifetime, system power consumption. So if I want to increase the lifetime, I have to decrease the power requirement. Very simple way. But for that, people are working in the electronics sites, and nowadays different types of batteries are also being coming up to have a very higher lifetime. Fuel cell, thin film batteries are being explored. Bidirectional wireless communication is essential for the implantable devices. And for that you have AM, FM and other pulse modulation. Different techniques are used. But particularly when this communication we are talking here, you have to see that when the signal is going inside the body or it is coming out from the body, it has to go through the different tissue level. Okay, tissue layers. And in those tissue layers, there will be some absorption. So that your signal level will be drastically reduced. That is the main problem. I cannot increase the signal level very high. Okay, whatever at the inside, whatever signal is generating, it is very small. And if I want to transmit, then it will go through the different tissue layers. It will be absorbed, and finally when it will come, it will be very, very small. It will not be detectable. And from the outside, if I want to send it, the inside, then I cannot send a very high signal. The tissues will be affected. So we have to think on that. Particularly, say today, people are, if you have some that devices, pacemaker. Pacemaker now battery life has increased a lot. More than 10 years, 20 years, it is available. But initially, people also thinking that if I can transmit the power and recharge the battery from the outside. For that, what you require? You require a RF. Now RF, by RF, if I want to transmit the power, the inductor will be very, very large. That is the main issue here. I cannot have a very large inductor inside the body, in the implantable device, pacemaker. But if I reduce that inductor, you will not get that much of power. Okay. So these are the issues. And globally, people are working on that. Globally. Okay. So biomolecular process, I am just escaping these ones, some of the slides. Some of the MEMS devices that can be used for the micro robotic surgery, for the nerve cell operation, and some of to get the signal from the nerve cell, from the neuron, you have to use the MEMS devices. A MEMS needle, it can penetrate and go to that accurate position of that nerve cell, and you can get the signal out of that from the nerve, from the neuron. Okay, people are working on that. Now you can think what is the neuron size, and then consider what should be the needle dimension so that it can detect that signal. So it is in that level, submicron. Secondly, biocompatibility. That is another issue. Okay, it should not be very, very hard material. If you go on stick, the nerve will detach. So you require polymer. Now polymer is coming up. Okay, earlier it started with a silicon. People have done, you can see different paper, published paper, silicon needle that is being inserted and getting the signal back. But today people have gone to the polymer material also. Okay. Then for the robotic surgery, actually people are using the quartz material for automatic robotic surgery. Why? Because with that micromachining, you can get a different shapes of the quartz. Now you can insert it, and by the electrical signal, you can actuate that quartz, and you can cut it very precisely. You can cut it. Monitor through the. This is all about your through the catheter-based operation. You can use it. Monitor through the CCD camera, and doctors can cut that tissue very, very accurately just by giving a signal to these devices, quartz devices. If you give the signal, it will vibrate and it will cut the tissue very, very precisely. Okay, so these are the some areas I'm just talking. So cutting tools, scalpel and all. This is another one, drug delivery. A microneedle. You can see the area of microneedle. It is being just passed over the finger tip. And probably you have also heard the automatic insulin injection in the blood. You have a complete system which just take it as a watch. Just it is in the at the wrist. It detects what is the blood glucose level. Okay, by that device, it through the electrochemistry process, it detects what is the glucose level. If it is more than certain level, or it is already programmed in the chip. If it is more than some values, 150, okay, then automatically the insulin will be injected in the blood. For that, what you require? For the detection, glucose detection, you have those circuits. Okay, electrodes and all, electrochemistry, your enzyme, and that will detect, generate the current and see what is the glucose level. Now, if it is more than that, then what you have, you should have a insulin. You should have the insulin tank, storage tank, and that is also there. And then micro pump, and also some micro needle is required. Why micro? So that signal will come to the micro pump. You start on, and micro pump will be switched on, and by that, using that micro pump, a micro or nano liter volume of that insulin will be injected through this micro needle in the blood. So this is a complete. This is called a complete system. SOP, system on package. This is just one. It is now commercially available also. May not be in the India, but in the outside, in the Europe and USA, it is available, and it is just like a wristwatch. Okay. Yeah, yeah. Insulin is stored there. That probably they have something, probably. Yeah, probably. Is at the environment you will not get that low temperature, but probably they have something, and that way it is. I do not know.
Micro freeze is needed.
Yeah, micro freeze it is required then. To preserve that. Yeah, probably that it is there.
New issue, micro freeze.
You can think of these new devices. This is another endoscopy with a lab on a pill. You have a capsule, and if you take it, then while it is going through that, you will get all the images at your outside tape recorder. What you require? You require a camera, you require a light source, a digital camera, light source, battery, radio transmitter, MEMS sensors for temperature sensor, pH sensor we require. While it is moving, we have to get the pH value, because it is required for the different disease diagnosis process. So it is all incorporated in this capsule. Okay, and some of the Israel group already they have produced that. Some Israel group already they have in the market. Now coming to our activity, BioMEMS activity. One is that to detect the cardiovascular diseases. Okay. Here one problem is that the disturbed blood flow at the arterial bifurcation is considered to be an indicator of the vascular oxidative shear stress that promotes the initiation of the progression of the atherosclerosis. What does it mean, atherosclerosis? we know that if you take a high level of cholesterol, then some fats or cholesterol that will be accumulated in the artery, and that blocks the artery, and finally it goes to the heart stroke. So heart attack. Now what is happening in a tube? If something blocks, then the flow of the blood will be disturbed. Okay, and if it is more than the 70% of that the diameter, then it is a very severe case. Really very serious, severe case. So can I detect that? And what is the operation to remove this? They are using some catheter tube. Either in a one way it is by the open heart surgery, or if it is a major more than 70%. But if it is a low level, then you can do through the catheter also. What they do, use this catheter, and by balloon angiography and all, they do this operation. They remove this stenosis. The stenosis means the deposition of the cholesterol or fat at the blood vessel. You can remove the stenosis by this catheter process. Can I implement a flow sensor at the catheter tip? Catheter means it is just a very thin polymer tube, I can say, in a very simple way, which is biocompatible, and it is very standard, device available in the market. So catheter tubes for this this type of surgery, its diameter is about 1 to 2 micron. 1 to 2 micron it is the diameter, and it is go through these blood vessels and comes over here. And while it is coming, can I measure the blood flow? For that, I have to implant a blood flow sensor at the catheter tip. And here I cannot use the silicone. I want the catheter, the device should be wrapped around the catheter. And while it is moving, it will measure the blood flow. I cannot use the silicone because silicone is a hard material. I want a polymer material. A polymer material should act as a substrate. On that, we will have that flow sensor device. For that, we are working over that, and so we started with a MEMS-based flow sensor, a cantilever type, and hot ammeter, where if you have a hot wire, that actually hot wire means you have to pass the current through the wire. Then it will radiate the heat. Heat will be radiated out. Now, if there is a flow from this side to this side, then the heat will also flow from this side, okay? And the flow can be measured by monitoring the resistance of this hot wire, okay? So this is called the hot wire ammeter principle, and we have tried to implement that and get that sensor. So at the catheter tip, this hot wire device will be implemented using a polymer, and when it will be inserted, then the current will flow through that. Its resistance value will changes depending on the flow of the blood, and if you can monitor the resistance value, you can say what is the flow pattern. Now, when there is a normal blood vessels, a normal flow will be there, and you will get some change of resistance. But now, if you have a stenosis or a blockage, then in that places the flow will changes. Flow pattern will changes. As the flow pattern will change, the heat radiation from this sensor, it will changes. As the heat radiation changes, the resistance value also changes. So whatever you will detect, the delta R, you will get it for the normal flow condition. The delta R value at the turbulent flow motion, it will be different. And from that, we can say here it is the stenosis. Here it at this location you have the blockage. Okay. So by real-time monitoring during the catheter insertion, by real-time monitoring of the flow pattern, you can say where is the location of your stenosis. Okay. Hmm. Hmm.
microbiology.
Hmm.
So what will be the dimension of that hot bias?
Yeah, that is the for the, by microfabrication process. You'll get it. I'm coming to that. So we started with some of the design. You use the silicon, this, that, and as I told, I will wrap around, the sensors will be wrapped around the catheter tip. It should not be a straight one. So we took around the a periphery, this length is the periphery of the diameter, over that we have made this register, Mienner line structure, to get a very total length will be very high. And this resistor material is your nichrome. Okay. Now if you send the current through that, it will be heated up, and this is some of the simulation results with the blood flow. Okay. And you see the how is that with the change of the pitch value of the resistor, how the heat will heat distribution will changes. Here you will have a, if the pitch value is more, the distribution is not much. Sorry, the distribution of the heat is non-uniform. And if you decrease the pitch value, you will get more or less uniform temperature distribution over there. So this is some of the, with this design, and then you can use what should be the substrate. Whether I will use the silicon dioxide nichrome or glass nichrome or PDMS. We require the PDMS, and for that what is the power requirement and all we have calculated. And one thing we have to be careful that as it is we are inserting in the blood vessel, the temperature rise of this resistor heater should be within the 6 degree to 8 degree centigrade. It should not be more than. If it is more, sensitivity will be high, but I cannot do that because your blood cells will die. So it has to be within the 6 degree centigrade. So some more simulation we have done using the flow. So from the here we have used some electrical model of the console to get the heat distribution and all these things, power requirement. Oh, it is working. Simulation is in the electrical domain. After getting that results, you come to the microfluidic domain. Okay, and to get with the flow what is the heat distribution and all these things. And here another thing is that what is the temperature profile during the flow. Okay, and it should be the transient response also we have to see. What is the uniformity around the catheter area. So all these things has been done by the simulation process, and we do all these iterations until we are satisfied that yes, these results can be taken. And once we do that, I'm not going into the details of that. And another important thing is that the blood flow, it is pulsatile in nature. It is not a uniform flow. You will have this flow. So what is the input velocity? And this is the velocity and the temperature, how the temperature will varies, and that is also up to the 6 degree maximum rise. Then with the change of flow pattern, this temperature will also changes within the plus say 2 degree centigrade changes are there. So all these simulations has been done using the different domain. You can use the console, you can use the other softwares also definitely. Okay, but here you have to integrate that. Once you do in the electrical domain, if you go in the microfluidics domain or mechanical domain, that merging you have to do it carefully. Otherwise, if you don't do it carefully, because it deals all with the equations, if you cannot do it without any understanding, if you do, you will not get a good results. You cannot interpret that results. So you should have that knowledge. Okay, when what we are using, when we will use, and all these things. Otherwise, any software, any value you give, you will get some value. You will get some output. Whether it is a correct or wrong, you have to analyze it properly. And in these cases, as you are using it is a multi-domain software, so you have to be very, very careful. Okay. Probably in the morning session in the console, you have done some of these things. Now coming to the fabrication part. So we have used a PDMS. PDMS is the polydimethyl siloxane. This is one of the polymer, and this is the chemistry part. What is the bond and all? You have a silicon bond, and along with that you have a CH3 bond. Why we have chosen this? Because it is available in our lab, and we can do the processing. And also another thing is that it is biocompatible. Okay, that way we have taken this material. But most of the very good biocompatible polymer is your perylene. Okay, but processing of perylene is quite difficult. You should have that, and we do not have that facility over there. So PMMA is also there. Yeah, you can use it, but it may not be. I think it may not be very. Yeah, it is a biocompatible, but it may not be that much flexible as we require. So these are the different issues. So we have used started with the PDMS, and let us say use a PDMS layer. Over that we will have a nichrome heater by thin film deposition process and lithography process, and I can use that. But when we started, first we found that the surface of the PDMS is hydrophobic in nature. What does it mean? Hydrophobic means it will not stick the water because of this CH3 bond. And as it is a hydrophobic in nature, if I deposit a nichrome film over there, any film, not only nichrome, any film, if I want to deposit, it will not be adhesion problem will be there. It will not be compatible to the MEMS fabrication. So this is the first issue, first problem we have faced that. Okay. So what we can do, to come to the chemistry part, forget about all the microfabrication, mechanic and all. Now you have to come, how I can remove the CH3. So chemistry is involved. So we remove the CH3 by using some or treating in the oxygen plasma. If you treat it in the oxygen plasma, this one will be removed, and finally you will get the wedge bond over here, which is a somewhat hydrophilic in nature. Okay. So people, not only us, people are also doing using the oxygen treatment, oxygen plasma treatment, or plasma treatment, or you can use the wet chemical treatment. Just with a nascent oxygen to generate by the wet chemistry, and that nascent oxygen will come over here and make this bonding process. Okay. So this is the one thing. Then the other one is that this is all the fabrication process, fabrication of this PDMS. I'm not going into the details. Just you pour those materials and spin it, you will get the uniform layer of the PDMS, and then you can peel it off. Okay. As when we will process, you have to process on something. Although finally I want it should be a flexible, but initially when you start, it is a liquid. So I have to use some glass substrate. You can use a silicon substrate. A hard surface is required. Okay. Then on that you spin coat, and then you do the oxygen plasma treatment and all these things. They have done different how the hydrophilicity is coming out by using the contact angle measurement and all. Then they have done the FTIR studies. What are the bondings are present? Chemistry has gone again. Whether the CH3 has been replaced or not, that can be analyzed through the FTIR studies, and this result confirmed that things. Now coming to the thin metal deposition, thin film deposition. In our case, the material is your nichrome. Nichrome means it is a 80% nickel and 20% chromium. It is a material we have chosen because it has a very high TCR value. Temperature coefficient of resistance, it is quite high. That's why we have chosen it. But the maximum you can change, you can get it probably, it is a platinum. Okay, but we use this material. Now, although this one has been changed to OH bond, if I just deposit it, but after deposition we have seen there are a lot of buckles and cracks over the film surface. Okay, lot of buckles are there, and also the cracks. I can show it here, not visible that side. Here you can see these are all the cracks, and in between the surface of the flame is wavy. That's why we call it is a buckle. Those things are called the buckles. Okay, it may be a random buckle, it may be a very smooth or regular buckles. Why it is happening? Although we have changed this CH3 bond to OH bond, because of the mismatch of the Young modulus. It is a polymer, very low Young modulus. The nichrome film, it is a two orders more Young modulus. So this is a huge mismatch. If I use a silicon, it is a very good. Addition will be good and all these things. So these are the issues. Okay. So, and due to that you have a compressive stress, and for that you will have the buckles. Yeah, here you have a good picture. This with that flame, deposited film, we did the lithography and we get the pattern, but finally you have all these cracks and all. Okay, so the power was about 120 watt. This is the condition. With the 90 watt, this is the condition, and with the 60 watt, we found that it is much better. Okay, and this was deposited by the sputtering technique, and for the sputtering, this is the power, base pressure, sputtering pressure, and then we have taken these parameters and changed a lot with the different combinations, and finally we have achieved the good flame without any cracks. If you have a cracks, then the continuity of the flame will not be there, so it will not act as a resistor. If you have a buckles, we can accept that, but it should not have any cracks, because cracks means it is a physically there is a separation, so no electrical continuity. But buckles means the surface you have some waviness only, but film is continuous. So and these buckles at this different these parameters, we got a regular buckles and we get a continuity over the register pattern, and there is no cracks over there. So these are all the research we have to do. Okay. So these are this is the fabrication process and all, and finally, so you have started with some glass or a silicon substrate. Over that you have developed these sensors, and after fabricating, completion of the fabrication process, you have to now detach it from the substrate. I can do just by peeling, you can separate that, but that again it will destroy the structure also, because it's a very thin film structure. So use some chemical, it is with a PVA solution. These things will be, the PVA solution has been coated here, and over that all these things has been done, and finally if you dip it in water, PVA will go in dissolve in the water, and these things will be floated. Probably we have these pictures here. This is the fabricated silicon or PDMS substrate, and release PDMS sensor chip here. After final fabrication, you can see the main line, and these are the bond pads, main line of the different structures, and finally this is the one device, separated device, and that has been separated by dissolving the PVA in the water solution. Okay, and now once it has been done, then you release the structure or device, then you have to go for the measurement purpose. Now we have just initiated this measurement step of these devices by putting it under the probe station and sending the very high velocity fluid through that and measuring the your resistance. So with the temperature change, what is the resistance change we are getting it? Okay, and probably with the temperature we are doing using the IR heating, or we can also do the heating by sending the current to a nearby heater. Not in the main heater, but to the nearby heater we send the current and measuring the resistance changes to the second sensor. Okay, and this is some of the plot, because we have just started this measurement, and this is just at the under the microscope we have done and with the airflow, but finally it has to be implemented in a catheter, and then this is some of the pictures we have implemented probably in the catheter tube, and they have just started the measurement, and these are the some of the results, and finally we have to do it in vivo using some animals and all. This should be the total target. Okay, then only it can be taken up further. Before going to the human, it will ultimately it will come to the human body. So before that it has to go through the different level of testing. Not that directly I can put it in a human body. You have to go through the different animal testing and all. Okay. So that's why for any BioMEMS devices, biomedical devices, from the lab to the commercialization, it takes lot of time, lot of years, 10, 15 years. It has to pass through the different category. Okay, and then it will come to the market. In between, it does not meet those category, those points. It will be discarded simply.
How it react around the
that we are now doing it, trying. Now for the initial measurement, we are just doing with some kind of a glue, and that glue should be biocompatible again. And here, what we are doing, just you have a bottom, you have a PDMS substrate. On that, you have a nichrome. This nichrome will be exposed to the blood vessel, but that should not be. On the top of that, we will again coat the PDMS, thin layer of PDMS. Yes, PDMS is biocompatible, but nichrome is not, so we have to protect that. And if I have a very high thickness of the PDMS layer, then heat transfer will not be. I require much more power, so those things we have to optimize. So measurement part technology, the fabrication technology has been standardized, but measurement we have to do still a lot. Okay. Now coming to the other one, the DEP, just simply very in a short way, I just tell, DEP means dielectrophoresis. What is it? A cell, it is a neutral particle. Okay, a biological cell, it is a neutral particle. So you have a same number of positive ions, same number of negative ions at the surface. Okay. Now, if you have a uniform electric field, these is two are the electrodes, and in between these two electrodes you apply a electric field, you will have a uniform electric field over here. So if I place a biological or a neutral insulated particle over there, due to the same distribution of charges, the net force acting in both the sides is equal. Okay, both the sides, the net force acting on the cell is equal. So particle will not move. Now consider a non-uniform electric field. Non-uniform electric field, how will generate? This is one electrode and this is one electrode. You apply a voltage, so you will have a electric field like that. So here you have a maximum electric field, here you have a very low electric field. Now if I place this neutral particle over here, depending on the permittivity of the media as well as of the cell, these forces F1 and F2 will be different. And so particle either will move this side or this side, either in the low electric field side or in the positive electric, high electric field side. and that way we distinguish positive DP force or negative DP force. Okay, so we can utilize this. We can utilize this to separate the biological particles. A biological cells, it have a membrane, you have a cytoplasm, nucleus and all. Now you have some that is the biology part, you have a proteins and all those things, DNA and all. Now you have some electrical equivalent of the biological cell also. A membrane is taken as a capacitor. Cell membrane is taken as a capacitor. Okay. Cytoplasm part, cytoplasm is inside, that is taken as a resistive component. So by that way you can make a equivalent circuit of a cell. Now as you, it has some material, so it has some permittivity also. Permittivity, resistivity you have in the cell. For all the biological cells, it comprises all those protein and all, but you have that a permittivity, a dielectric constant, it has a resistivity, conductivity also. Now you consider when a normal cell is transforming to a malignancy, a cancerous cell, a disease progression is taking place, and today we are just thinking there is a change in the biochemistry pathway. Protein is changing, and that way it is going from normal to malignancy. But if we consider that not only, although the biology part is changing, but at the same time your all those non-biological parameters, electrical parameters, that will also changes. Definitely it will changes. Okay, so can I detect that non-biological parameter? What is the change in the permittivity of the cell? It will changes. What is the mechanical property, the Young modulus? That will also changes. Can I detect that? So all the non-biological parameter, particularly the mechanical property, electrical property and the optical property of the cell, that will also changes with the disease progression process. Okay. But today the biotechnology, it is mainly confined to their testing. What are the protein and all those changes are taking place. That way it is definitely it is a gold standard, but this is the new domain. Electrical, non-biological parameters also changes, and that way can we detect. Now here it is just how I can separate a normal cell with a cancerous cell using the dielectric property. If you have a biopsy sample, there you have a normal cell, there you also have a cancerous cell. It is a mixed. And in the after biopsy, you take the sample, it will go through the different cell culture, and then by antibody antigen reaction, it detects whether it has a cancerous cell or not. It takes lot of time, lot of days, because you have to do the cell culture, and you have to use lot of chemicals and all that. So it is also a very costly process. So now, can I separate the normal cell from the biological cell, normal cell from the cancerous cell, using this dielectric property of the cell? Because by the disease progression as it is going from normal to cancer, definitely there is a change in dielectric property or resistivity or whatever. So this technology is called the dielectrophoresis process, and by that process you can get a changes, a separation of those particles. And as if you can separate those particles, then you can have some other testing and you can say whether it has a cancer or not. So for that, what you require? You require a non-uniform electric field like this, like this. So here in this platform, here we have shown that this is the inlet side and this is the outlet side. In between you have a 3 electrodes. One electrode is quite big, and these two are the very thin electrode, and it is passing from inlet to outlet side. Okay, and this electrodes is on the plane or on a glass substrate or on a silicon substrate. This is just a cross sectional view I have shown. So this we call the planar electrodes, and after fabrication of the planar electrode, you can have a microfluidic channel over this, okay, like this. So all over this you will have a microfluidic channels, and then you can make a holes to get a inlet and outlet. Now you apply, you send the samples through this inlet channel, and as it moves from here to here, normally you will have a laminar flow, and by the velocity vector it will go out of this. But now while it is moving from inlet to outlet side, you apply a electric field between the ground, this is the ground electrode, and this is the active electrode, either this one or this one, both can be also be used. So by this process, by applying this voltage, you will have generate a non-uniform electric field over this region. The maximum electric field will occur along this length or this length, and minimum electric field will occur over here. So now the particle is moving from here to here. So while it is moving, it will experience either a positive dP or negative dP. If it is a positive dielectrophoresis force, then this particle will move continuously, moving to this side and go in this way, or it will move in this side and go in this way, because the dP force is acting in this direction, either in this or that direction, and velocity vector is in this direction. So resultant it will be like this. And if it is a negative dP force, then particle will have a will accumulate at the low electric field region, and so it will move in this way. Now what is this positive and negative dP? It will depend on the dielectric properties of the cell as well as the media. Media is fixed. Now you have a normal, so its dielectric property is fixed. Now if you have a normal cell, it has a dielectric property, it will may have a positive dP, so it will go in this way. Now a cancerous cell comes, it has a other dielectric property, it will experience a negative dP, so it will move in a straight way. So that process you can separate the normal and malignant cells. Now there are a lot of questions. What is the change or of the dielectric constant that it can detect? That means it is a sensitivity. At what sensitivity level it will separate those. Whether 100% separation I can achieve, or 80% or 50%. Those things we have to establish. Okay. This is the process. Final. This is the final device. You can see this is the electrode. Electrode is made of what? For the biological samples, I should have a noble metal that will not react. Which will not react? Yeah, I cannot use the aluminium. Platinum also, yes, definitely you can use it. So this is the gold metal electrode, and over that you have a micro channel, which you cannot see it here, but this is the inlet and this is the outlet. Okay. Now, sorry, this is the outlet and this is the inlet, and inlet you have to connect to the syringe pump, so that the sample can be inserted through this syringe pump and through this inlet to this channel, and while it is going, you can apply the electric field and the particle will be separated out. Okay, this is the larger view. Here you can see the microfluidic channel. This is the one, the boundary lines, and this force also depends on the frequency. You can use the DC, but if you use a DC field, joule heating will be more, cell will die. So better you use the AC field. And with the AC field, that dP force, it will depend on the frequency also. And we have observed that probably this is the previous HeLa cell. HeLa is a cancerous cell, cervical cancer cell, and with this we have started some of the experiment, and we have observed that at 100 kilohertz it shows the negative dP, whereas if we apply if the frequency is 1 megahertz or more than 500 megahertz, we observe that the HeLa cell will have a positive dP, and that's why it will go in this way, in the other two direction. If it is a negative dP, then it will go in this way through the middle channel. Okay. So this is some of the results you can see here. Do you have that video? No. Okay. Okay, limit. I'll just so this here also we have to do lot more testing. So far we have done only with a one type of cell, and we have seen that this cell manipulation, I cannot say it is a separation, I can say only that it is a manipulation of cell at a different frequency. Okay, that we have observed, and later on we will mix up with another cell and we can do the separation. So and by that way you can also do the light cell and dead cell, because they have a different dielectric property. You can separate it. You can separate the red blood cell and white blood cell using the DP process. So a lot of things people can do using this. So I think, and also these are some other things I will not discuss much. Some bioimpedance study. After cell separation, when it is going out, you can measure the impedance. The impedance value also changes, and that impedance is a signature of what is the cell. Okay, give some indication. So we are doing some kind of research using this, and some other things I will not discuss. Let us stop over here. Okay, some microfluidics channels. So challenges are the biocompatibility, life of the device, retrieving data out of the device, resist the drifting along with the body fluid. So a lot more things we have to do. Okay, I'll stop here and thank you for your patience.
Thank you, sir, for your nice talk. Now, I request Mr. Devashish Maji to come and present some memento. So here we end today's session. Now, tomorrow again our session will start from 9. So, as usual, the car will be there around 8:30. So here we'll again meet. And tomorrow the first talk will be the MEMS electronics interface circuit by Professor Siddhartha Sen. Then our lab visit and the demonstration will be there. Okay. And another announcement that those who are interested to collect the receipt, so they can collect. It is with the Rajlakshmi Chauhan. So you can collect now or tomorrow also. And tomorrow also we'll distribute the certificate. So thank you for your patience, because as MEMS, it's very difficult to accumulate all the lectures and all the area in 3 days, but we have tried to accumulate all the things. So maybe the time has exceeds, but thank you for your patience. Thank you. Sir, thank you, sir.